Good day. Today we're going to talk about motion in space. Motion in space. In this section, we show the ideas of tangent and normal vectors and curvature can be used in physics to study the motion of an object, including its velocity and acceleration along a space curve. As we saw when derivatives were introduced, if r of t gives the position of a particle at time t, then the velocity vector of the particle at time t is v of t equal to r prime of t. That is, the velocity vector is also the tangent vector and points in the direction of the tangent line. The speed of the particle at time t is the magnitude of the velocity vector, that is, magnitude of v of t. Thus, we have v of t, no vector, equals the magnitude of v vector of t equals the magnitude of r prime vector equals ds dt. That would be the rate of change of the arc length. Here, I want you to notice the difference between the v magnitude function, which stands for velocity, and the v vector function, which it represents the vector function inside the magnitude. Similarly, the acceleration vector is a of t, which is the same as v prime of t or r double prime of t. All these formulas are just as you'd expect them based on what we learned back in the first quarter of calculus. Example 1. Find velocity, acceleration, and speed of a particle with position vector r of t equal to t squared I plus 4tj plus 4 ln t k. And this would be, there's a slight typo here, this would be find the velocity, acceleration, and speed of a particle with position vector given. So solution is not that difficult. So to find the velocity, this will be v of t, which is equal to r prime of t, or it looks like we'll have 2t, comma 4, comma 4 over ln of, 4 over t, not 4 over ln of t. There's our velocity function. If we want the speed, it will be the magnitude of this velocity function. So the velocity function will equal the square root of 2t squared plus 4 squared plus 4 over t quantity squared, which would be the square root of 4t squared plus 16 plus 16 over t squared. Perhaps this will simplify. It seems unlikely, but it's perhaps worth trying. So this would be, if we gave ourselves a common denominator of t squared, this would be 4t to the 4th plus 16t squared plus 16 all over t squared. And let's see, does that first term factor 2 and 4? I think it might. I think that might be a perfect square. So is this the square root of 2t squared plus 4 squared over t squared? I think it is, which in turn would be equal to just 2t squared plus 4 all over t. So there's our speed function. Notice what's important about this is that this is a scalar function. It's not a vector. And finally, the question asks us to find the acceleration. So we can do this kind of continuing on, and we get that the acceleration is a of t, which is r double prime of t, or just the vector valued function 2 comma 0 comma looks like negative 4 over t squared. So there is our velocity, acceleration, and speed of the particle with the given position function. Example 2, find the position vector of a moving object that has acceleration 2I plus 12tj, velocity at 0 equal to 7I, and position at 0 equal to 2I plus 9k. This question is similar to one that I believe we did a few sections ago, where we simply need to find some antiderivatives. So we note that the velocity will be equal to the antiderivative of the acceleration, which would be the antiderivative of 2, 12 t, 0 dt, which would be 2t plus 2t, 6t squared, and then antiderivative of 0 would be 0. But then we've got to remember a constant c. And the c is a constant vector. So this whole thing is our v, and we note that that v has to, at 0, has to be equal to 7i. So the next thing we do is, this is kind of step 1. So to step 2, we need to find that c vector. So we'll solve for v of 0, which will be, this is substituting into the velocity vector that we just found. So that will be 0, 0, 0 plus c, and that must be equal to 7, 0, 0. So here's the v of 0 that we were given. And so it should be pretty clear that c must be 7, 0, 0. And we conclude this step with v of t equals 2t plus 7, 6t squared, 0. And that plus 7 is coming from the constant vector that we found. Okay, so we've now found our velocity vector. Now we got to move one step up and find our position vector. So 3, we want to find the position vector r of t. That'll be the integral of the velocity vector. That is the integral of 2t plus 7, 6t squared, 0 with respect to t. And that will be t squared plus 7t, 3, 2t cubed, 2t cubed, and still 0. But now it's plus a new constant. Maybe we'll call this new constant d. All right, step 4, we need to find that d. And so we remember that we have r of 0 equals 2i plus 9k. And so in step 4, we want to find, that's a d vector. We want to find the d vector. And so we need to solve r of 0, which based on the thing we just found would be equal to 0, 0, 0 again, plus d, but must also be equal to 2, 0, 9 from the green vector above. So this tells us what our d vector is. It tells us that our d vector must be 2, 0, 9. And so we're able to conclude therefore, we can conclude that our r of t function must be equal to the r of t that we found, t squared plus 7t. But we got to remember the terms that are in the constant d. So plus 2, and then 2t cubed, and then what do we have? 0 plus 9, or just 9. And again, notice that the 2 and the 9 here are coming from that d constant vector that we found. So the question asked us to find the position vector of the moving object. Right here, we wanted to find this position vector, that is, find r of t. And sure enough, we found r of t. If the force that acts on a particle is known, then the acceleration can be found from Newton's second law of motion. The vector version of this law states that if at any time t, a force F acts on an object of mass m, producing an acceleration a, then F equals ma, or F of t equals m times a of t. Example 3. What force is required so that a particle of mass 100 kilograms, just for the record, that's a heck of a big particle, has the position function r of t equal to t cubed I plus t squared j plus t cubed k, where r is in meters and t is in seconds. And there's a little typo here. This should be r is in meters, plural. All right, how do we solve this? Well, recall that F equals ma, or force equals mass times acceleration. And so since we're given the position, this tells us that we could also find our velocity. If this is the position, then the velocity must be the derivative of the position, or 3t squared, comma 2t, comma 3t squared. And in turn, the acceleration be the derivative of the velocity, or 6t, comma 2, comma 6t. And so we can put these things together. And so we know our acceleration in the formula. It's this guy right here. We also know the mass. That's the 100 kilograms. So thus, we get the F of t will be equal to 100, the mass we're trying to move, times the acceleration vector of 6t, comma 2, comma 6t. So here's the force required to move this superparticle. This will give me the force. Tangential and normal components of acceleration. When we study the motion of a particle, it is often useful to resolve the acceleration into two components, one in the direction of the unit tangent vector and the other in the direction of the unit normal vector. Let's draw a picture before we get too carried away. So we're trying to figure out what's going on with our acceleration vector at some given point. Here's our acceleration. And so we're going to break it up in two parts. Part of that acceleration is going to be in the direction of t, that unit tangent vector, and the other part is going to be in the direction of n, the unit normal vector. We're going to call the length of the part that's in the direction of t the tangential component of acceleration, and we're going to call the part that's in the direction of n, the length of that vector, the normal component of acceleration. So let's see how we can find a formula for this at and an, so to speak. So what follows is a derivation. This is a derivation for a formula that gives us a new way of thinking about acceleration. So we're going to start with the formula that t of t, the unit tangent vector, is equal to r prime over the magnitude of r prime. This is great, but we could write it in terms of, we're talking about motion here, and so we remember that r prime of t is the velocity, and the magnitude of r prime of t is the speed. So this tells us that t is equal to the velocity vector divided by the speed function. So the top here, this is velocity, and the bottom, the denominator, this is the speed. And I'm going to try to use that little curvy v to help make it clear that I'm talking about speed or v. We could multiply both sides of this by speed, and we would get a representation for our velocity vector. So our velocity vector is equal to the speed times the unit tangent vector. Okay, now we got to be a little bit clever. We're trying to find something about acceleration. We have something about velocity, and we remember that acceleration is the derivative of velocity. So at this stage, let's differentiate both sides. Differentiate both sides. So we're going to get ddt and ddt of the velocity vector is equal to ddt of the speed times the unit tangent vector. Now on the left, the derivative of the velocity vector is the acceleration vector. On the right, we have a product, and so we have to use our product rule. So we will get the derivative of the speed times the unit tangent vector plus the speed times the tangent vector derivative. Oh my gosh. At this stage, we need to recall something. So we're getting there. Notice that this v prime in front of the t, that would tell us how much of the unit tangent there is in the acceleration. So we're definitely moving in the right direction, but we don't like that t prime. So at this stage, we need to do a little bit of memory work. So recall that we defined the curvature in a number of different ways, but one of the ways was as the magnitude of t prime divided by the magnitude of r prime. Okay. We could then solve for the magnitude of the t prime. And so we get that. So this tells us that the magnitude of t prime is equal to k times the speed function. Notice here, magnitude of r prime, that's our speed function showing up again. Okay. And also, so here's one thing we remember. We also want to remember that n is defined as t prime over the magnitude of t prime. It is. Also recall that n is equal to the magnitude of t prime divided by, t prime divided by the magnitude of t prime, which would tell us that magnitude of, which tells us that t prime equals the magnitude of t prime times the n vector. Okay. Well, notice here that we have a formula for t prime in both cases. So here's a formula for that includes t prime, and over here we have a formula for t prime. And so combining these two things, we now can have, we know that t prime is equal to k times the speed and it's also times the normal vector. So notice, make sure you're seeing where these are coming from. So the kv is this same kv here, and the n is the same n there. So if we all this jazz, okay, put my colors a little bit, all of this jazz can be substituted in for this t prime. Therefore, we're going to get that a is equal to the speed derivative times the unit tangent vector plus k, now it's the speed squared, times the n vector. And here we give these things special names. We give the derivative of the speed function the name at, or the tangential component of acceleration, and we give k speed squared the name an, or the normal component of acceleration. That is, at equals speed derivative an equals k speed squared. And in so doing, we have broken up our acceleration into its tangential and normal components, just like we talked about in the picture up at the top. All right, let's try to understand this better through a little animation. So notice that here in the beginning, our acceleration seems to be pointing kind of away from the curve, kind of into the bendy part. And you can imagine a car driving around here and you'd feel pulled sort of into the middle, and then switches around as the curve shifts. And so again, we're being pulled into the curve, if you will. And we could ask how much of this acceleration is in the direction of travel and how much of this acceleration is perpendicular to travel. So the normal component, sorry, this is the tangential component, says like there's places where you seem to be going relatively straight, and so the tangential component, the red part, is relatively long, but there's other places, everywhere where there's lots of bends and turns, that tangential component is relatively short. So tangential component short on the bends, and it's conversely, when you're going around those bends, notice that there's a pull towards the middle, right? When you're going around a windy road, there's a lot of stuff pulling you into the door, throwing you into the door, or throwing you into your seat, into the lap of your neighbor. But when you get to these straightaways, the normal components get shorter. The blue one gets shorter. The blue one's getting shorter because your acceleration is forward and not side to side. So I hope that gives you a little bit more of a picture of what's going on with this tangential and normal components of acceleration. So let's look at what this means. The first thing to notice is that the binormal vector is absent. Again, we're looking at this formula here, that a equals the speed derivative times the tangent vector plus the curvature times the speed squared times the normal vector. So there's no binormal vector. No matter how an object moves through space, its acceleration always lies in the plane of t and n. That would be the osculating plane. Next, we notice the tangential component of acceleration right here. Tangential component of the acceleration is the derivative of the speed. That is the rate of change of speed. And the normal component of the acceleration is the curvature times the speed squared. This makes sense if we think of a passenger in a car. A sharp turn in a road means a large value of the curvature k. So the component of the acceleration perpendicular to the motion is large, and the passenger is thrown against a car door. As elsewhere, there are alternate versions of this formula, but this simple version, a equals v prime t plus k v squared n, serves most of our purposes. Here, a sub t represents the tangential component of acceleration, and an represents the normal component of acceleration. Example 4, decompose the acceleration vector r of t equal to t squared, comma 2t, comma ln t into its tangential and normal components. So for a solution, it pays to look ahead. So we want to think about a of t as being the tangential component of acceleration times t plus the normal component of acceleration times n, with the tangential component being equal to the speed derivative and the normal component being equal to the curvature times the speed squared. So let's make a list of all the things that we're going to need to find in order to make this happen. So we need, let's see, looks like we're going to need the speed, not u, pardon me. We need the speed function. We're going to need the speed derivative. We're going to need the curvature. In order to define the curvature, that's going to require that we find r prime and r double prime, along with some magnitudes. And then we're going to need to find the tangent vector, which is going to require us finding, again, r prime and magnitude r prime. Okay, those thankfully we might have already found for the curvature. And we also need to find the normal vector, which is going to require that we find t prime and magnitude t prime. Let's see if we went back in the same vein to find the velocity, or I should say the speed vector. That means we need to find the magnitude of r prime vector. And the speed vector derivative would be the derivative of the one we just found. So phew, looks like there's lots of derivatives that we need to take, and then we're going to need to put these things all together. Let's start working. So let's see. So we know that r prime will equal, looks like 2t, comma 2, comma 1 over t. We know that r double prime will equal 2, comma 0, comma negative 1 over t squared. This means we could find the magnitude of the cross product, or rather the cross product of r prime cross r double prime. And I'm finding this for the sake of the curvature. So that's going to be, it looks like negative 2 over t squared, comma, I'm going to have, oh, let me put my minus sign in place. So it looks like I've got negative 2t over t squared minus 2 over t. To get my signs right, let me just check again. Negative and minus, okay, I think I got my signs right. Comma, and then minus 4. We could simplify that. This looks like negative 2 over t squared, comma, plus, this is going to be, t cancels, minus 2 over t, minus 2 over t, minus 4 over t, so plus 4 over t, comma, negative 4. All right. So let's see. So what do we need next? It looks like we're going to, what have we found? We've got 1, 2, 3. So now maybe 4. Let's find the magnitude of r prime, which is also the speed function. So this would be the square root of, looks like we've got 4t squared plus 4 plus 1 over t squared, which we could find a common denominator here. This would be equal to 4t to the 4th plus 4t squared plus 1 all over t squared. That numerator looks like a perfect square, 2t squared plus 1. So this will be the square root of 2t squared plus 1 squared divided by t squared. Or this is just 2t squared plus 1 over t. So we found our velocity function. If it helps, this could also be written as just 2t plus 1 over t. Okay. So we have our r prime magnitude or our velocity function. We also need 5. We need the magnitude of r prime cross r double prime for our curvature. So the magnitude of r prime cross r double prime will equal the square root of first term squared. So I have 4 over t to the 4th plus 16 over t squared plus 16. And once again, we got to do some simplification. So finding the common denominator, this will be 4 plus 16 t squared plus 16 t to the 4th all over t to the 4th, which once again, it looks like a perfect square. So I have 2 plus 4t squared squared over t squared squared, which is 2 plus 4t squared over t squared, which is a funny way of writing. Looks like 2 over t squared plus 4. All right. So of the things that we're looking for, let's kind of go back and check in with our list. What have we found so far? We found the velocity function. We found our r prime magnitude. We found r prime. We found r double prime. We have not found the stuff. We haven't yet found our curvature. Let's see. So we've got the top one. We haven't found most of the top critters quite yet. So let's see if we can find those. Maybe we'll start with our curvature. So our curvature, make sure I can see everything that I need. So our curvature, this is number 6, is going to equal the magnitude of r prime cross r double prime. So this will be 2 over t squared plus 4, all divided by the magnitude of r prime, which is, let's see, 2t plus 1 over t quantity cubed. And believe it or not, I'm going to not simplify that. I don't see a real benefit. 2t plus 1. Yeah, I don't see a real benefit in simplifying it at this point. I think I'm just going to leave it that way. Maybe we'll have to be forced to come back and deal with it later. 7. I need to find my unit tangent vector. And it's going to be r prime divided by the magnitude of r prime. So I'm going to have maybe I'll write my magnitude, my 1 over my magnitude as t over 2t squared plus 1 times the r prime vector, which would be 2t comma 2 comma 1 over t. Whew, that's a little bit of a bear. So I went through and solved this question using the formulas on the previous page that I said were sufficient. And after working on it for a while, I realized that it would work, but it wasn't nearly as sufficient as I thought. So let me add a couple of questions to our repertoire, rather a couple of formulas to our repertoire that will make our lives a little bit easier and a little bit cleaner. So again, we have that, that we can write the acceleration as the acceleration in the tangential direction times the tangent vector plus the acceleration in the normal direction times the normal vector. Or if you like, we could write this as v prime t plus k v squared. So v here, k v squared times n. So those were our 2 representations we had for breaking the acceleration into its tangential and normal acceleration components. Well, a couple of formulas make this a little bit cleaner. So much cleaner than that v prime formula. So we can, for our at, we can add a couple formulas. So we can have at is equal to r prime dot r double prime all over the magnitude of r prime. And so this is another formula for that tangential component of the acceleration. And we can also have, we can get that, and a n, or the normal component, is the same thing, but now cross product r double prime over the magnitude of r prime. Since it's the cross product and we want to turn it into a scalar, it's got to be the magnitude of our cross product. And so here the an, or the kv squared, could be written as all of that jazz there. So these are 2 formulas for the tangential and the normal component of acceleration, and these ones are a little bit easier to work with than what I gave you earlier. Again, practice makes perfect, and so hence you see a new different background in this part of the video than you saw in the earlier parts. So let's dive into our example. So in example 4, we're asked to decompose the acceleration vector of r of t equal to t squared, comma 2t, comma ln t into its tangential and normal components. So here's that tangential component, that's the yellow stuff, and the normal component, that's the blue stuff that we're looking for. So rather than using the formulas that we were given previously, we're going to use the two that we were given here. The reason why they're better or more efficient is because they allow us just to find r prime and r double prime, and we don't have to kind of go in circles back and forth between t's and v's and r's, which just kind of gets circular. So here is our solution. So what we're going to do first is we're going to find our r prime of t. So r prime of t is going to be 2t, comma 2, comma 1 over t. And then we're going to find r double prime of t equal to 2, comma 2, comma 0, comma negative 1 over t squared. All right, so this found me both of the vectors that I want. Now I need a dot product, a cross product, and a couple of magnitudes. I'm going to actually start by finding my cross product, just because of the way things are written. So 3, I'm going to find r prime cross r double prime. And I'm finding this because it will help me find that blue formula. So magnitude of the first bit is going to be negative 2 over t squared. Over t squared. And then comma, minus sign is built into the formula. And so we have, looks like minus 2t over t squared. And then minus 2 over t, comma, it looks like we have minus 4, which it looks like could simplify to what? It looks like we have minus 2 over t squared, comma, a 2 can cancel, or a t can cancel in both numerator and denominator. So I have minus 2 over t, minus 2 over t, minus 4 over t. It's all negative, so I've got a positive 4 over t. And then it looks like I have minus 4. And it looks like there's a common factor of 2 throughout that. If we could take out, which might make our lives a little bit easier. So this will be 2 times negative 1 over t squared, comma 2 over t, comma negative 2. Okay, so that's my cross product. Now we can go ahead and find our dot product. So r prime dot r double prime will be 2t times 2, or 4t, plus 2 times 0, or 0, plus 1 over t times negative 1 over t squared, so it's minus 1 over t cubed. All right, so I've got our, let's see, we can probably simplify that a little bit if we give it a common factor. That would be like 4t to the 4th minus 1 over t cubed. Okay, so we have our dot product, we have our cross product. Now we've got to come through here and find some magnitudes. So let's start by finding r prime magnitude. So 5. So we want the magnitude of r prime. So the magnitude of r prime is going to be the square root of 2t squared, which is 4t squared, plus 2 squared, which is 4, plus 1 over t quantity squared, which is 1 over t squared. And we could find a common factor here, which would be of t squared, or sorry, we could find a common denominator. So we'd have 4t to the fourth plus 4t squared plus 1 all over t squared. Notice that this numerator is equal to, it looks like a 2t squared plus 1 squared over t squared. And so we get that it looks like our r prime magnitude is going to be 2t squared plus 1 all over t. So we have r prime, r double prime, r prime cross r double prime, r prime dot r double prime, r prime magnitude. All we have left to find is our r prime cross r double prime magnitude, which will be the square root of, it looks like I can pull this 2 out front. So I'm going to just put that out front as a 2. I know it'll just be chilling around. And then underneath the radical, I've got negative 1 over t squared squared, which would be 1 over t to the fourth. And then plus 2 over t quantity squared, 4 over t squared, plus negative 2 quantity squared, which would be 4. Common denominator of t to the fourth. So I have 2 times root 1 plus 4t squared plus 4t to the fourth over t to the fourth, which would be, looks like 2 times root. It's a perfect square in the numerator, so we have 1 plus 2t squared squared over t to the fourth. So all told, it looks like we have, looks like 2 times 1 plus 2t squared, 1 plus 2t squared, all over t squared in the denominator. So that is our 6 things we need. Now we got to put them together to find our tangential and normal components of acceleration. So let's go back to the beginning so you see those formulas. So our AT, or our tangential component of acceleration, so AT will be equal to r prime dot r double prime, which would be the 4t to the fourth minus 1, 4t to the fourth minus 1 over t cubed, and then we're going to divide by the magnitude of r prime, which is the 2t squared plus 1 over t. And remember, we could just invert and multiply. So we're going to multiply this by t over 2t squared plus 1. 4t to the fourth minus 1 itself is a perfect square. So that's like a 2t squared plus 1 times 2t squared minus 1. We could cancel a t here. And our denominator now would be t squared times 2t squared plus 1. The 2t squared plus 1s are going to cancel. And we're just left with at equals 2t squared minus 1 over t squared. So there's our tangential component of acceleration. Right there. Now we got to find our normal component of acceleration. And an is the magnitude of the cross product, which would be 2 times 1 plus 2t squared over t squared times the magnitude of r prime, but we can just multiply by its reciprocal. So now we're going to multiply by t over 2t squared plus 1. T will cancel. I don't think anything else is going to cancel. And so what we're left here with is 2 times 1 plus 2t squared all over t times 2t squared plus 1. And so from all this stuff, we also noticed that our acceleration vector is equal to, well, so we found our at and our an. Now we're just trying to make sure we know how to write it. So we know that our acceleration vector, thus the a vector will equal the tangential component of acceleration, which is 2t squared minus 1 over t squared times the t vector plus 2 times 1 plus 2t squared over t times 2t squared plus 1 times the n vector. Here's the yellow. Here's the blue. And we've written our acceleration vector as a product of the, or as product, in terms of its tangential and normal components of acceleration. The only thing we haven't done is we haven't found the t and the n vectors, but we have done this elsewhere. I guess I would, for the purposes of this particular question, I'm going to leave it here because I think that in most of these cases, at least in terms of homework examples or assessment questions, finding the t vector in terms of t is fine, but finding the n vector is an awful lot of derivatives. And so probably wouldn't find this n vector unless we were given a specific point at which we were going to do that. So let me back out. Here's the whole question in its entirety. And there you have this nice, simple, clean, and kind of fun lesson on motion in space.